Let us try to understand some important concept of K-map. Okay, so K is stands for actually Karna. So Karnaugh, Karna map. Okay, so this is what the name of the person who has given this concept of K-map. So first thing is why K-map is used or why somebody should learn K-map. Well, so we have already seen that importance of logic expression minimizations. So to have a simpler design of hardware, to have more speed, to have less participation, you want to minimize a logic expression. So one of the way to minimize logic expression is Boolean algebra. So another way to do the same task is K-map. So why we should study K-map? So although we have Boolean algebra, see student, there are certain drawbacks of Boolean algebra. Like Boolean algebra is not systematic. So you have seen we have solved couple of questions in Boolean algebra. So in most of the questions I was saying if you do like this, this will happen. If you do like that, this will happen. But it was not a method oriented process. It's like more and more property you have, if and more shortcuts then you can solve those problems. So there is no such systematic way. So we want to have a systematic way that if I follow step 1, step 2, step 3 like this, I'll be ending to the answer. So Boolean algebra is not a systematic approach, but K-map we'll see this gives a systematic approach to minimize a logic expression. Point number 2, there is something known as don't care combination. So what is don't care means in certain digital system for certain input combination output is not defined. So in the digital case, whenever I am saying that it is undefined, so in a digital system the output could be always either 0 or 1. So whenever it is undefined, we really don't care what it is. So we say it is don't care. So in Boolean algebra, we don't have any provision to handle the don't care combinations. So if you have don't care combinations, we go by K-map approach. So two major reasons. One is it gives a systematic approach to solve a problem. Secondly, it handles don't care in a efficient way. All right. So these are few points regarding K-map. Let us have discussion of this before we go into the actual process, how K-map is formed and how to use it. So first thing is it's a graphical tool for minimizing logical expression. It's a graphic tool because the K-map it looks like this. So these are the maps actually. So using these maps we will be minimizing logic expression. So it's a graphical tool for minimizing logic expression. We don't have to write big equations. So by doing some mapping kind of things or grouping kind of things in a map, we can get the expression. K-map can give the final answer either in SOP or POS form as per requirements. So we have seen in the Boolean algebra, like a function can be represented using SOP form or it can represent using POS form. So K-map also having the provision. So if you want the answer in SOP, you can make use of K-map accordingly. If you want the answer in POS, you can again make use of the K-map accordingly. If a function have don't care combination, K-map is preferred for simplifying the function. K-map is suitable up to 5 variables. So generally in GATE exam, so 99.99% of cases we get the question up to 4 variables. Only one question is asked in GATE 2016 of electronics, of which is a 5 variable K-map questions. So generally we'll like we deal K-map up to 4 variables, some cases up to 5. Beyond 5 it is complicated. So K-map is not used beyond 5 variables. So what is the technique then to solve the problem if we have 6, 7 or 10 number of Boolean variables? In that case we make use of something known as Queens-Mackley method or tabular methods. When number of variables are more than 5, K-map is not convenient because of complexity. Boolean algebra also it is having complexity, so we make use of tabular method to handle those cases. So let us see some features of K-map. In any K-map having n variables, total 2 power n number of cells are present and every cell is meant for a particular fixed mean term or max terms. What is the meaning is students? So first of all, in K-map we have some predefined structure. So like 2 variable map is used to handle the Boolean function which comprising of 2 variables. 3 variable map is used to handle Boolean function comprising of 3 variable. 4 variable map is used to handle the Boolean function comprising of 4 variables. Now the point is, so if a K-map is, if you want to use the K-map for n variable cases, then the map contains 2 raised to power n number of cells. Like for a 2 variable case, the map contains 2 power 2, 4 number of cells. So you can see we have 4 number of cells, basically 4 boxes. Similarly, if we use 3 variable map, so we have 2 raised to power 3, 8 number of cells. So you can see we have 8 number of cells. If you are using this for 4 variable case, we have 2 raised to power 4, 16 number of cells. So number of cells in a K-map is always 2 raised to power n, where n indicates number of Boolean variables. N indicates number of Boolean variables. Okay. Now students, remember in the K-map, okay, so you can see that I have written some number 0, 1, 2, 3, 0, 1, 3, 2, 4, 5, 7, 6, 0, 1, 3, 2, 4, 5, 7. So like this the numbers are written. What it means is, I'll explain from where these numbers are coming. What it means for the time being is, you just take it granted, or you just believe it, that so in every K map, each cell is reserved for a particular mean term or max term. If I want to get the answer in SOP form, then I'll be using the mean terms. Suppose the function having mean term, let's say 1, 2, 4, 7. Suppose these are the mean terms of a function. So while using the K map, I should know which particular cell is meant for mean term 1. So this cell I'll be talking about. Then mean term 2, I'll be talking about this for 4 and then 7. These are the cells I'll speak about. So any K map, its corresponding mean term position or max term position is fixed. If you are using in soft format, so this number indicates the place of the corresponding mean terms. If you are using POS format, this number indicates corresponding max term places. So if you are using in POS format, so if this is 7, it means that this cell is meant for max term 7. If you are using in soft form, this cell is meant for using mean term 4. Okay, similar the story for this as well. So remember students that something known as gray code. Gray code is used in formulation of K-map. Okay, gray code is used in formulation of K-map. In an n variable K-map, each cell is logical adjacent to n number of cell. What is the meaning of this statement? Let us see. So first thing is gray code. Okay, gray code, this is a concept that you study in the binary codes. For the time being, you understand this way. Like if I am writing the gray code for 1-bit case, it is 0 and 1. If you write the gray code for 2-bit case, in a 2-bit case, I can represent 0, 1, 2, 3. So 0 having gray code 0, 0, 1 having 0, 1, 2 having 1, 1 and 3 having 1, 0. I am not finding the binary equivalent of these decimal numbers. These are the gray codes. So that's why, so for 2 variable case BC, I am writing its corresponding gray code in this sequence 0, 0, 0, 1, 1, 1 and 1, 0. It is not 1, 0, 1, 1. Okay, note that it is 1, 1 followed by 1, 0. So this is what is the gray code written, and this is what the gray code written. For 1 variable case, this is the gray code. For 2 variable BC, this is what the gray code. Then what I am doing is inside this box, okay, so I am writing the value of A followed by BC. So the pattern is ABC. So let's say for this cell, A value is 0, BC value 0, 0. So you get 0, 0, 0. For this cell, A value is 0, BC value 0, 1. So you get 0, 0, 1. So you see that the first value is A. So first value is 0 in all these cases. Then the second two value are BC. So this is 0, 0. This is 0, 1. This is 1, 1. This is 1, 0. Yes or no? Similarly, for the second row, here A value is 1. So the first value is 1 everywhere. Then BC value 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Okay. Now, if you find the decimal equivalent of these or binary combination students, what you get? You get 0, you get 1, this is 3, this is 2, this is 4, this is 5, this is 7 and 6. You see these are the numbers I have written 0, 1, 3, 2, 4, 5, 7, 6, 0, 1, 3, 2, 4, 5, 7, 6. So this is how these numbers are coming. So you need to remember this pattern. Like in a 3 variable case, this is what is the pattern is. I'll explain you by taking some questions how to make use of K-map to solve some questions, we'll see. But this number you should definitely remember. For 4 variable case, so this is what AB and this is what CD. So like here I have written the pattern is A followed by BC. So here for every cell, I am writing AB followed by CD. AB followed by CD. So like in the first row, this row, so AB value, first value is A, next is B, next is C, next is D. So first value is AB. So AB 0, 0 for this row. So you see it is 0, 0, 0, 0, 0, 0. Then CD is 0 0, CD is 0 1, CD is 1 1, CD is 1 0. Similarly, for this row, let's say your AB value is 1 1. So you see 1 1 1 1 1 1 everywhere. Then the corresponding value of CD is written here. 0 1, this is 0 1, this is 1 1, this is 1 1, this is 1 0, this is 1 0. Like this. Now, if you find the decimal equivalent of these binary numbers, what you get? 0 1 3 2 4 5 7 6. Then this is 8, not this one, right? 8 9 11 10, then 12 13 15 14. You see that you see 0 1 3 2. So 0 1 3 2 4 5 7 6 4 5 7 6. Then 12 13 15 14. If you find the decimal equivalent, this is 12 13 15 14. Similarly, last row is 8 9 11 10. 8 9 11 and 10. So this is how it happens. So from where these numbers are coming? These numbers are coming using the concept of Greek code. And we don't want to go into again too much of detail. How this arrange, that arrange. If you see some standard textbooks, you'll find the logic. But anyway, it is not necessary. What is important for you to know, I'm just explaining that. So I hope this is clear to you that how we are getting these numbers. Okay, so this pattern you should definitely remember. These structures and this number you should remember. Similarly, if you do the same task for two variable case, it is 0 1 2 3. Okay, so this is for two variables, this is for three variables, this is for four variables. We are going to see these three categories. All right, now students, we make use of an important concept. There is something known as subcube. Okay, so you need to understand subcube. So what is the meaning of subcube? We'll see. See, listen here. So first thing is, in K-math, I think in your BTech you must have studied that while solving the question on K-math, we used to do some kind of grouping. I believe you might have seen some this kind of grouping, somewhere this type of grouping, somewhere this kind of grouping. We do this kind of grouping. But if I ask students why you are doing this grouping, based on what, so they don't have the answer. Some people say that I can make a group like this. This is 4 cell collections. I can make a group like this. But if I ask, can I make a group like this? They say no. No, sir, we cannot do a grouping like this. But if I ask why you cannot do a grouping like this, then they don't have the answer. Or can I do a grouping like this? No, they say no. But why? They don't know. Or if I ask you, can I do a grouping like this? They say no. But why no? They don't know. So let us try to understand what is the rule to make the kind of grouping. Okay, so so to know the concept of grouping, you should understand the concept of subcube. So what happens is, in a n variable K map, collection of 2 raised to power k number of cell forms a subcube. So in a three variable case, okay, collection of 2 power k number of cells. So if k value is 0, 2 raised to power 0 is 1. If k value is 1, 2 raised to power 1 is 2. If k value is 2, 2 raised to power 2 is 4. If k value is 3, 2 raised to power 3 is 8. Okay. Similarly, in a 4 variable case, so 2 raised to power k equals to 0. So then it is 2 cell, 2 equal 0 is 1. Na? This is 1. K equals to 1 if it is 2 raised to power 1 is 2. K raised to power k equals to 2 means 2 power 2 is 4. This is 4. Similarly, for k equals to 3, it is 8, and k equals to 4, it is 16. This is for k equals to 3, and this is for k equals to 4. So let us first discuss regarding the 4 variable case. You can easily understand the 3 variable case. So in a 4 variable K map, so n value is k here, n value is 4 here. In a 4 variable K map, collection of 2 power k number of cell. So when k equals to 0, you get 1. When k equals to 1, you get 2. K equals to 2, you get 2 power 2 is 4, and so on and so forth. So whenever I am saying that in a n variable map, collection of 2 raised to power k number of cell, it means collection of 16 cell or 8 cell or 4 cell or 2 cell or 1 cell. You don't have collection of 3 cell, collection of 7 cell, collection of 5 cell, not that way. So whenever you are doing a collection, it must be in the form of 2 raised to power k. So these are certain rules we need to understand before we go into the solving process of the K map. So first thing is, the collection should be 2 raised to power k. So it could be 1 cell, 2 cell, 4 cell, 8 cell or 16 cell, not anything beyond that. Okay. So in a n variable K map, collection of 2 raised to power K number of cell forms a subcube. Okay. So I can say, so collection of 2 cell, this is a subcube. Collection of 4 cell, this is a subcube. Collection of 4 cell, this is a subcube. This is also a subcube. This is also a subcube. Then collection of 4 cell, this is also a subcube. Okay, like this. You can have your own way to find these subcubes. Okay. So, but this subcube is said to be a valid subcube. This subcube will be valid if inside 2 power k cell, each cell will be logical adjacent to k number of cells. Now, suppose for example, students, so for understanding purpose, so let me take collection of 4 cells. And the 4 cells, let me take this way. This is what is the collection I am taking. This one, okay. So, this is a subcube because collection of 2 raised to power k, collection of 4 number of cells. I want to know whether it's a valid subcube or not. So, how to know it is valid subcube or not? So, the condition says each cell will be logical adjacent to k number of cells. Now, what is the meaning of this term logical adjacent? This is important. So, remember 2 cells are said to be logical adjacent cell if there is 1 bit change in the corresponding gray code. So, suppose if I ask you whether these 2 are logical adjacent cell, you need to check if I am observing the bit pattern, how many bits are changing. So, yes, these are logical adjacent cell as well as physical adjacent cell. Why? Because if I am observing the pattern, only the middle bit which is 0 that is changing to 1, remaining bits are same. So, these 2 are logical adjacent cell as well as physical adjacent cell. So, if I ask you whether these 2 are logical adjacent cell or not, answer is no. These are, you may say it is physical adjacent cell, but they are not the logical adjacent cell. Why is that? Because if I am checking the bit pattern, now 1 is 0 here, 1 bit change here, and this 0 is 1 here. So, there are 2 bits are changing. The condition is there should be only 1 bit change, strictly 1 bit, not 2. So, although you may say these are physical adjacent cell, these are not logical adjacent cell. Can I say these and these are logical adjacent cell? If you see the bit pattern, first bit is 1, okay, 1. Second bit is 0, this is 1. So, 1 bit change, third bit is 0. So, how many bits are different among this and this? Only the middle bit. So, yes, this and this are logical adjacent cell. Can I say this and this are logical adjacent cell? So, 0, 0, 0, it is 1, 1, 0. No, 2 bits are changing. They are not logical adjacent cell. And in a n variable K-map, students, remember, each cell is logical adjacent to n number of cells. This point also I have written here. Gray code is used in formulation of K-map. In a n variable K-map, each cell is logical adjacent to n number of cells. Suppose if you ask me, sir, for this cell, what are the logical adjacent cell? So this one, this one, this one. Left, right, bottom, 3. If you ask me for this one, what are the logical adjacent cell? For this one, what are the logical adjacent? This one, and this one. You check this 1 bit change property satisfying or not. If I ask you what are the logical adjacent cell for this, and these 3. Any cell you take arbitrarily, it will be logical adjacent to 3 number of cells. Similarly, if I am going with a 4 variable case, let's say if I am asking you for this cell, what are the logical adjacent cell? 1, 2, 3 and 4. Generally left, right, top, bottom, side. Diagonal pattern if you take, it doesn't satisfy. If I ask you what are the logical adjacent cell of this? 1, 2, 3 and 4. So you can check it. So for this one, if you see, if you compare the bit pattern of this with this and this, only 1 bit change you can find. Similarly, if I ask you for this one, how many logical adjacent cell you have? Again the answer is 4. What are the 4? 1, 2, 3 and 4. So these are the 4 logical adjacent cell. So any cell you take, it will have 4 logical adjacent cell. Okay, so we understood what is the meaning of logical adjacency. Now let us see how to identify valid subcube. So my goal is to tell whether this is a valid subcube or not. So I will be saying it is a valid subcube provided inside this collection each cell will be logical adjacent to k number of cells. So for this collection k value is 2. So for this collection k value is 2. So I need to check for each and every cell there should be 2 logical adjacent cells. So if I check for this, so this is logical adjacent to this and this. Okay, no problem. This one is logical adjacent to this and this. But you see, we know that this is having 4 adjacent cells this and this. But out of 4, only 1 is present inside this collection, remaining 3 are outside this. So for this condition of valid subq is not satisfying. So inside this collection, I need this cell should be logical adjacent to 2 number of cell. We know for each and every cell it is logical adjacent to 4 cell. But in the collection, I want it should be logical adjacent to 2 cells, which is not happening. So similarly for this also there is a problem. For this and this. So these are 4 adjacent cell, but out of 4 only 1 is present inside this collection, remaining 3 are outside. So for this also not happening. So if you check for this, it is happening, or if you check for this, it is happening. But it is not like that. So for each and every cell, it should satisfy. So this is not a valid subq. So that is why this kind of collection is not eligible for grouping. So in the K-map, if somebody asks you, so why can't you do a grouping like this? Then you can say this collection is not a valid subq. So grouping can be done by considering the valid subq only. Now let me take some other kind of pattern and let us try to explain whether it is satisfying the valid subq or not. Now suppose let me take collection of 8 cell. Suppose if I am taking the collection of 8 cells. So let's say this is what is the collection I am taking, collection of 8 cells. So in this case, my value of k is equals to 3. Value of k equals to 3. So I want inside this collection, each cell will be logical adjacent to 3 cells. Okay. So whether it is happening or not, let us check. So this one is logical adjacent to this and this. Yes. This one is logical adjacent to this and this. So this one is logical adjacent to this and this. This one is logical adjacent to this and this. So any particular cell you consider here, you see inside these collections, it is logical adjacent to 3 number of cells. So yes, this is a valid subq. So we can do a grouping like this. Okay, you can do a grouping like this. Or if you take a collections, maybe can I do a grouping like this, like this? Can I do a grouping like this? Yes, this is also a valid subq because, so again here k value is 2. K value is 2 means for each cell you need 2 logical adjacent cells. For this and this is present inside this subq. So fine. For this and this is present. For this and this is present. For this and this is present. So yes, each cell is logical adjacent to 2 number of cells. So this is also a valid subq. So we can do grouping like this. In the same arguments, you can do the grouping like this also. So this 8 collections is again k value is 3. So each cell will logical adjacent to 3 cells inside this collection. So you can do. Okay. So that's why students, in a 4 variable map, I believe many of you might have seen we can do a grouping like this. So this, I mean the 4 corner term, we can do a grouping like this, because if you see, this is again k value is 2 because collection of 4 means k value is 2. So this is logical adjacent to this and this. So yes, so for this it is satisfying. So if I am checking for this is logical adjacent to this and this. So this is also satisfying. If I am checking for this is logical adjacent to this and this, satisfying. If I am checking for this is logical adjacent to this and this. So yes, so the collection of these and this is also a valid subq. So a grouping can be done by considering the diagonal element in a 4 variable map. So remember students, each and every time we don't need to do all these subq checking this all things. So you need to understand, if I am taking collections of cell, continuous collection of cell in a horizontal pattern or in vertical pattern, so they always by default satisfy the valid subq property. So I can take the grouping like this, horizontal way, continuous collection of horizontal cell or continuous collection of vertical cell. Even the sidewise collection also it will satisfy. Sidewise means maybe like this or like this, maybe like this or like this. or the diagonal one. So these are the valid subQs. Similarly, in the three variable map also the same story again. So can I do a grouping like this? Yes, you can do, because here the value of k equals to 2. So if k equals to 2, you can check whether this is logical addition to 2 cell or not. Yes, this and this. Any cell if you take, it is having 2 logical addition cell inside its collection, so we can do it. So can I do a grouping like this? I cannot do, because this is not a valid subQ, because so that property is not getting satisfied. So in this video, we understood why K-map is used, what is its utility, and the standard format of 2 variable, 3 variable, 4 variable map, and the concept of subQ, which will be used for grouping.